Okay, everyone, last chapter, chapter 18. This is on reactions of benzene, continuing with that. And one more time, remember, benzene's different from just a regular alkene. Alkenes, very easy to react them with Br2, but benzene being conjugated, not so easy because it's so much more stable. Really needs to have some extra boost in order to get that to react. So benzene's so stable compared to alkenes because of aromaticity and resonance delocalization. So in order to get benzene to work, though, it turns out that you can do that. You just need to add a catalyst. So catalyst, if you recall, is something that will help lower the activation energy of a reaction. So in this case, we can add in addition to Br2, a kind of Lewis acid catalyst named iron tribromide or iron 3 bromide. And so then we will be able, only with a catalyst then, be able to get our bromine on there. Okay, so how does that happen? What is this and how does that work? So first I mentioned it's a Lewis acid. That means that it likes to accept electrons. So when it accepts electrons, it can accept them from the Br2. Now when the Br2 pushes its electrons onto the iron, it makes this complex. And with this complex, you could see that the bromine becomes positive as it makes a bond to the iron. What that does, though, is it brings the electron density of the other bromine closer to it, and it makes this bromine positively charged as well. So it doesn't just fall off usually, but it does make this complex. And so you can think of it as a Br plus ion, which is really different. Usually when you think about bromide, right, every bromine we've had so far is bromide, right, pretty much. So this is the opposite, and that's because of its interaction with this Lewis acid. So whenever you see these guys then, okay, think of what's going on here and just pretty much think of it as, quote, Br plus, even though that's not just floating around by itself, it's something that you can think of. So let's write a mechanism then using that Br plus. So we start with benzene and we want to explain how do we get a Br on here? How does this reaction work? So first I'm going to say, well, let's sort of think about this and use this Br plus instead of this, because that's what is the result of all that. So if I have a, quote, Br plus, then that means my nucleophile is the benzene ring and my electrophile is the Br plus. Okay, that means that this is a kind of nucleophilic attack, but also eventually it's going to be a substitution reaction. So, and I'll show you why that is. So that bond is no longer there. We're going to form it either here or here, so you can pick one of those positions. Put the bromine there. Whichever one you don't pick gets a positive charge. Now here's the thing, this is not stable because it's now positively charged carbon. So I want to try to neutralize that, but I also broke my aromaticity. Here's aromaticity and it's broken here. So I want to regenerate the aromaticity there. So what I'm going to do is take a base in solution, and right now I'll just use B for base, and I'll just grab that. But you might ask, you know, what is the base? Usually it's going to be a bromide. So if you have FeBr3 turn into FeBr4 minus, then now these bromines are negatively charged and they can come back and grab that H. So I'll just show it in parentheses here. You can just write B if you want, but FeBr4, and so one of these bromines can come in and then we'll end up with FeBr3 again. And you probably remember from Gen Chem that catalysts get regenerated. Now this is how FeBr3 turns into FeBr4 and then turns into FeBr3 again. And so if we do that, then we've regenerated our aromaticity, we have our bromine on the ring now, and you also ended up with an HBr from this step right here. Okay, so this reaction is called electrophilic aromatic substitution. We are substituting, there was an H right here, and we're replacing that H with a Br. So the benzene in this case is acting as our nucleophile, is attacking the species that we are creating here, so our reagents. Okay, so in this energy diagram, notice that we start out with some kind of a sigma complex, and then that leads to either the substitution product or it leads to the addition product. So that intermediate is this guy right here, and that is going to lead to either being more aromatic, which is of course thermodynamically favored and our driving force, or maybe we have bromine in solution or bromide in solution. Maybe the bromide here could attack here and we could have the dibromo addition product as well. It's a possible outcome, but you can see that we're really being driven by thermodynamics in this case. Now there's lots of groups here in red that you can see added to the benzene ring, so we need to learn how to make all of them. Okay, but it's actually not too bad. Okay, I'll tell you. Br2 with a catalyst of FeBr3, we just did that one. If we change it to chlorine, then just change it to chlorine, Cl2 FeCl3. So those are pretty simple. And then these guys here are similar as well, except instead of Br2, we have RBr, or we have an R group and some kind of a halogen. I'll just put X, it could be bromine or chlorine. And then I usually use, instead of FeBr3, I use AlBr3 or AlCl3. Okay, so aluminum tends to work better for these R groups. I could also add a carbonyl in an R group. So usually to do that, I need to have that group, and then again, some kind of a halogen attached, and AlX3 catalyst. So these are all very similar to each other. And then the last thing is if I want a nitro group, that comes from nitric acid and HNO3, and in acidic solution from concentrated sulfuric acid, H2SO4. Or if I just have H2SO4 by itself, then I could have a sulfonyl group added on. Okay, and sometimes we call it fuming H2SO4 because you can see fumes coming from it. It's so concentrated. All right, so your job will be sort of to learn each of these reactions. So what I recommend right now is that you just take out a sheet of paper and just write benzene, Br2 FeBr3, question mark. Okay, benzene, Cl2 FeCl3, question mark. What do you make? And then make another sheet and do benzene, bromobenzene, what do you need to turn it into that? Okay, so you can do what we just did here, which is leave the arrows blank and see if you can remember what those reagents are. Now the mechanisms are very similar to each other. So the nitration reaction is where we use nitric acid and H2SO4. So it's going to be the same type of mechanism, but it's going to be a little bit trickier though, because you probably wonder, where did the NO2 group come from? How did I get NO2 out of this? Okay, so to do that part, I just want to show it to you. I probably won't ask you to do it, but I'd like you to sort of have some background information about how some of this happens. So here's nitric acid, and maybe you didn't realize it looked like that. I always forget myself because I hardly ever draw these out, but here's sulfuric acid as well. Okay, so the thing that I'm looking for is I'm looking for an NO2 group, right? So just as a clue, you know, NO2, I'm probably going to use that kind of an NO2 right here. So ultimately, all this involves is making this OH group leave, and that's what the sulfuric acid's for. So I'm going to have protonation here from the sulfuric acid. So maybe in this color, I'll just grab. So maybe I'll just grab this H and do that. So this is just proton transfer, and then I'll end up with, this didn't change over here, OH, and then I had this protonation from the sulfuric acid. HSO4 minus is left over, and a positive charge here. So basically what's going on is I can draw some resonance here, or maybe I can do that and then show that. So that's going to give me an NO2 group, but it looks different from what I have in the benzene, right? Up here. That's actually going to be a little bit different, but here's this NO2 ion, NO2 positive charge. So that's my electrophile going into the aromatic substitution. So instead of Br plus as my electrophile, I've generated NO2 plus here. Okay, and that's going to explain how to get that group on there. So once I have that, then I can follow the same pattern as with bromination. So let's show that. So basically I have, so this is double bond O, positive charge on the N. So this is going to attack here and it's going to release onto the O. So then after that I'm going to get something like this, right? So there's my nitro group. And then I have a positive charge on this carbon here. So then what I need to do is take a hydrogen off and regenerate that aromaticity. And that's how I get to here. Okay, so it's basically the same kind of mechanism. Benzene attacks the group, the electrophile, and then that electrophile, I've broken aromaticity, so I need to regenerate it. So then I get that. So I saw the same exact kind of mechanism up here. Okay, so I want you to really look at those until you can see that they're the same mechanism, because that's going to help you explain all of these. The next reaction is the sulfonyl group here. So we do that with concentrated or fuming H2SO4, and then you can take that off with some dilute H2SO4 or water. So let's try this mechanism. So to do this one, it's a little bit more complicated here. H2SO4, actually your book shows this as SO3. So fuming H2SO4 is really SO3. And then when you have the benzene ring, it's just going to attack that. So like this. Now remember, sulfur can have an expanded octet, so that's why it looks funny. Okay, and then once you know that it's really SO3, then it's easy from there. So now you can just take a base and you can just regenerate the aromaticity right here. And then you can get this H on there by just proton transfer in the next step. I'll show you. So we generate the aromaticity, and then we have the two double bond O's, and we have this O minus. Now we just need to have some acid from H2SO4 to protonate that. So this is O minus. Okay, and then for this particular reaction, you can actually go backwards as well with dilute H2SO4, which means there's more water in solution. So with water, you can go backwards. So let's see if we can figure that out. So here's my sulfonyl group, and then with water. Okay, so at this stage, you could either deprotonate here with water first, because this is a strong acid here. Probably that's likely, although that's not going to help you too much to get rid of this whole group, but let's say you do that. And then we need to break that aromaticity, so I'm going to have H3O plus now to be able to do that. So let's write that. So this is going to grab here. And so I'm going to break aromaticity for a second here. And I have a choice of where to put that positive charge. I could put it here or I could put it here. But if I put it here, and the reason why I did that was because I could actually have this come in here and break and regenerate the aromaticity that way. So that allows me to regenerate the SO3 from the fuming sulfuric acid. And then I'll end up with benzene by itself. Okay, so I'd like you to go back through then and just take a little break and practice your mechanism, Br2, FeBr3, practice your mechanism for HNO3, nitration, H2SO4 sulfonation, and then in the next session we'll go through the alkylation reactions and acylation reactions.